Introduction to Geometric Distribution. Okay, so in grade 12, as you carry on with studying probability and probably doing the data management and probability course, you're going to run into these probability distributions. I did an introductory video with regards to probability distributions. I'll put up a link up above there in case you want to be able to watch it. And once we did that, I then started to carry forward into taking a look at the binomial distribution. I took a look at some, proving of the expected value for the binomial distribution. So I'll put up a link to the introduction to the binomial distribution up above there. I think it's very useful before you jump into this video. So if you understand the binomial distribution and now you're jumping into this, which is on the geometric distribution, it has basically the same assumptions. The only key difference is kind of the random variable is different, which makes it a geometric distribution, unlike a binomial distribution. But, we are taking on trials, okay? We have, basically, we're dealing with discrete probability distributions in here. And these trials are independent. Now, the two possible outcomes are, again, success and failure that we have. The probability of success is the same in every single trial that we take on. And I'll show you an example so that you can understand this like I did with the binomial distribution, because reading this, may not make a lot of sense, right? It will just start making sense once you start seeing the example. Now, the key difference for this geometric distribution is this fact that our random variable is the number of unsuccessful trials before a success happens, okay? And I'll show you what I mean that in just a moment. Now, the probability, okay, so the probability distribution, okay, so P of X is equal to, so we can map it up. Again, please remember this is discrete. So, X is going to take on 0, 1, 2, 3, 4, and so on. Okay, unlike binomial distribution, which had a fixed amount of trials, for the geometric, we're going to assume that we have an infinite number of trials, okay? Because technically, you can keep on going and having unsuccessful trials, pretty much forever as you carry on, right? The probability of that is practically approaching 0 as it carries on, but it's not technically 0, okay? So now, that X that we have, so our random variable, notice that it is the number of unsuccessful trials before a success happens. Okay? And then finally, the expected value is equal to 1 over the, 1 minus probability, okay, over the actual probability, where the probability is the probability of having a success. Okay? And I actually prove this expected value for the geometric series. For those who are interested, I'll put up a link up above there for you there. I'm not going to do the proof here because it does take a little bit of time. So now, what is this geometric distribution, right? Okay, so what we are referring to is the following. So if we had, okay, so this is, I'm just going to give you an example. So let's say our example is that we have, I don't know, let's say maybe a baseball player, and the baseball player is a pretty good baseball player and hits 300, okay? Which means that the probability, okay, of success for that baseball player, okay, so 300, which is really just 0.300, or it is 30%, which means 30% of the time that baseball player is going to get a hit at an at-bat. Which seems kind of low, but believe it or not, if you're successful enough that you're hitting 300, you're going to be a multimillionaire because it's actually pretty hard to do in baseball. So that would be the probability of success. So for instance, for our case, for this geometric, okay, distribution, what we would have if we mapped, so P, okay, of X, okay, we know is, so we have it right above there. And now, what we are talking about is the following. Okay, so P of 0 really means that at your first at bat, you're going to have 0 unsuccessful trials before a success, which means right at the first at bat, you actually get a hit. What's the probability of that? Well, the probability of that is just P, which is equal to, 0.3, okay, or 0.300 for this baseball player, right? Because we had 0, okay, so for this, our X was equal to 0. We had 0 trials, okay, of being unsuccessful. Now, if we wanted to have the probability, okay, where we have 1 unsuccessful attempt. So unsuccessful attempt, if the batter comes up, if they're unsuccessful, then we know that the probability of being unsuccessful is 70% of the time, right? But that would be at our first at bat. And that had to be multiplied by 0.3 because now that baseball player is successful on its first attempt, okay? Sorry, on its second attempt. So how many unsuccessful trials were there before that person got a hit? Only one. The first one was unsuccessful. And then we got a hit. So this X is equal to 1 right here. Where X is equal to 1 just means we had 1 unsuccessful attempt. And you can continue this. So the probability of having 2 unsuccessful would mean that we would have 0.7 on the first one, multiplied by 0.7 on the second one, and then we had a success. And that would have been for X is equal to 2. So in general, right, if we continued this, the probability of, let's say, at some attempt N, we would have N unsuccessful, okay, directly. So as we kept on going, okay, so it would have been 0.7 to the N, and then we would finally have a success. So that's for X is equal to N. And then you can continue this forever because I guess technically the probability is very low as you keep going, right? It gets lower and lower that you will not have an actual hit for a batter who's hitting 300 or has a probability of getting a hit 30% of the time. Now this makes it geometric. Now you may recall, right? So geometric, for example, expansion, right? Maybe you recall that from grade 11. I'll put up a link up above there, okay? Maybe to the geometric series, which is kind of helpful as well. So if you've run into this at some point, depending who your teachers were. And what makes this geometric is the fact that really this is an exponential, right? Now it's a decaying exponential because we have 0.7 to the n. And now exponentials, I'm sure that you've studied at some point in grade 11 and maybe even in advanced functions if you took it before taking a probability course. So this is just an exponential, okay, in fact. And this equation that we have right here, okay, is that exponential function. So if I'm going to copy this, I'll bring it down. This is in general what happens, that P of X for any number of unsuccessful trials is going to be 1 minus P. In our case, it was 30%. So 1 minus 30% is 0.7. Okay, to the X, okay, which is the number of unsuccessful trials. So you can have 0 unsuccessful trials, 1 unsuccessful, 2, and so on and so on. And the probability as you multiply these are going to get smaller and smaller. And this right here makes it exponential. So we have 1 minus P to the X, and then this P, really we could bring that to the front, right? So it would have been P, and then this would have been 1 minus P to the X, and this clearly is a decaying function. Let's actually graph this so that we can see this geometric distribution. So the geometric component is going to have this right here, where it's going to be this 1 minus the P to the X. That's what makes it decaying. And then this P really is just your starting point, right? Because when X is equal to 0, that means 1 minus P to the 0 is 1. And you're starting at P, which means the probability, in our case, let's say 30%, for the batter, right? On the first attempt, that's exactly the probability that that batter would have, okay, in order to be able to get a hit. So I want to plot this up into decimals so that I can show you how this distribution actually looks like. We can take, right, each individual right here. So if I was going to take it, so for P of 0, it's 0.3. Okay, for this right here, okay, this would have been 0.21, right? 0.7 times 0.3. And then I can continue, right, getting all of these and plotting them up for x is equal to 0, x is equal to 1, x is equal to 2. And now we would see what the distribution would look like. And you should see that based on this, it would be just a decaying function going all the way to 0, right? So let's take out, okay, so decimals right here. So I'm going to, okay, construct. So this is, you know, it's a sequence right here. So I'm going to have n elements. Actually, I'm starting from 0. So this is for my x. You know, I call this n at the moment. So, you know, let's say this was just one element. You know, we're going to go all the way up to, let's say, 10 elements at first. Okay, so 10 just simply means how many unsuccesses did we have, right? So we would distribute. Now, we have to go all the way to infinity. Okay, so I'm going to make this larger and larger and larger so that you can see that. You know, what else do we need? We need the probability of success. So probability of success is 0.3, I guess. Our probability is between 0 and 1, right there. We need our function. Okay, so our probability. Okay, so our distribution is, this was 1 minus p to the x and multiplied by p. Now we're going to restrict this, so x has to be greater or equal to 0. So we'll put that. Now this is a function. This is how the distribution would look like, right? So notice that's how it would be. But we don't have a continuous distribution. We have a discrete where we have 0, okay, unsuccessful trials, 1, 2, 3. So I need to map this correctly. So I need to plot these ordered pairs, f, and then substitute that in. And now you can see, so this now nicely shows us, okay, what happens. I can remove this. And that's our probability distribution. And that probability distribution, okay, would go on into infinity, you know. So, I mean, I can put that. But as you can see, you know, now it just gets closer and closer to 0, right? So as you keep going, you know, it gets smaller and smaller and smaller, okay, as you keep on moving along. So, you know, I mean, you can make this to 1,000, right? But it's not like it's going to help us in any way, because it's going to get closer to 0. So I'll just keep it at, say, you know, 10, because I think we get the gist. That would have been the distribution itself. Now, the summation of the distribution, because we're adding up the probabilities, should be equal to 1. And we can actually do that. You know, I can say sum. Let's see, I can't use, I'm going to use I for my index. It's starting from 0. All the way up to capital N there. And now we're summing up, we're summing up this. Okay, so there you go. It gives us a number. So 0.98, that's if we take the first 11 elements. That's the probability. But notice, if I, you know, instead of the first 10, I'll take 20. Notice 0.99, you know, 30. You know, it gets closer and closer. And I think you can, you know, this, notice it's rounded to 1, because that would have been the summation. And you see that in the corner there when you're taking the summation. So that's the distribution that we would have. And this is the geometric distribution in general. All right. So now if I go back here, so I'm going to go back right here. And if you wanted to know what the expected value is, the expected value, the calculation is very simple. It is just simply 1 minus p. So for example, for our case, the expected value is equal to 1 minus p, right, divided by p. So in this case, it's 0.7, 0.7, right, 1 minus 0.3, and then, sorry, divided by 0.3. okay, 2.33, that would have been our expected value that we would have, okay, in here. So for this, okay, so with that expected value, as I said, you could take a look at that link if you wanted to know where that proof comes from. Obviously, the expected value would have to do the summation, okay, so for x is equal to 0 times its probability, x is equal to 1 times its probability, and add all of them up. But that summation actually is nicely captured by this formula. So here is another example with the geometric distribution, where I'm going to come back to an example that I did with this, okay, except I did it with the binomial distribution. So the link to the binomial distribution with this example, I'll put up above there if you want to link back to it. But in here for the geometric distribution, so it says in a small town, the probability of finding a person that carries the Y28 virus is 2%. The probability is independent of the number of people in the town and the interconnection between them. Find the probability that the third person you talk to has the virus while the first two do not. Okay, so, this is an example of the geometric, okay, distribution when we're going to be graphing it, and you'll see that in part B. But let's say if I wanted to find the probability, so the probability really that the third person has the virus, that would mean probability that I have 2 unsuccessful, right, trials where I have, so now it's telling me that having a virus, so P, the small little p, is 2%, right? So 1 minus p is going to be 0.98%. So that means having 2 unsuccessful trials, or finding where the first person doesn't have the virus, second person doesn't have the virus, but the third person does have the virus. So that would have been the probability. So what's the probability of that? Let's take out the calculator here. 0.98 to the 2 multiplied by 0.02. Okay, and it's very close. 19208, or just 1.9208%. That would have been the probability of that. All right, so that's the first part A. And really it is coming from this, so 1 minus p to the x multiplied by p, except here x is equal to 2. We have 2 unsuccessful, okay, in this case, people that are actually virus-free. So for part B, so if I was doing part B, find and graph the geometric distribution, use decimals. So we just actually did decimals. So I'm going to bring decimals back in just a moment. So what we would have is, we would have to take this and we would have to graph it, right? To be able to find the distribution. So our P is equal to 0.02. So if I'm going to bring back my decimals here, so I'll put it and split the screen for this example. Let's put it at 10. However, so this is 0.2, and that's really the only change that I have to do to decimals in here. Let me split this out, okay? And you're going to see this. So it's going to start from that, and notice that it is, now it almost looks like it's a line, right, going down, and that's only because we have 10. N is equal to 10, right? So unsuccessful trials. Now that 10 worked very well when the probability was 0.3, because the decaying, the exponential decaying happened rather quickly. Now it's not going to be happening very quickly because P is equal to 0.02, which means that 1 minus, so 1 minus the P is 0.98. Okay, so this is really high, okay, and it's very close to 1. That's why it looks like it's kind of slowly coming down. Now, if I make this 100, right, so if you're going to start noticing this, if I make it 100, now you can see the exponential coming out. Now, the dots are so close together because I'm zoomed in on the x-axis there, and notice that if I make this 1,000, right here, and actually I can even graph, let me remove maybe this, okay, and graph the actual continuous function so you can see the decay, right? You can see the exponential decay rather quickly. So now if I graph back on the actual distribution, there you have it. So that would have been, okay, the way that we could graph it. And if you zoom in close enough, you can see that they're just dots all along the way. All right, now what's the expected value, right? So within here, that's the last question. Well, the last question, so that's not very difficult. So as that's C, the expected value for this is equal to, so 1 minus P divided by P, so 0.98 divided by 0.02. All right, so we can get what that is. So 0.98 divided by 0.02, and that is 49. All right, so that would have been the expected value, okay, within here. So, well, there we have it. That takes care of this particular example, and I hope that this is, okay, understandable for you in terms of introducing you to the geometric distribution, how it looks like. Most people will remember the formula. I do think that it's wise and worthwhile to understand the meaning behind this, and the key thing is that random variable, the number of unsuccessful trials before a success happens, right? So once you know that and you understand probabilities, it's not difficult to try to gauge this, right? If it's unsuccessful, you just take the probability of being unsuccessful, you know, on the first one, second one, third one, fourth one, and so on. And then eventually at the end, you have a success. So you multiply by that P, and then you have your probability distribution right there. All right, thanks for watching. We'll see you in a future video, okay? I hope this was useful. Bye, everybody. Cheers.